take absolute values, right? From the average, from Kendra and Linda's average, right? Take the absolute value. That was great, except nobody does it because it makes a hard point. Could we take the graph from Math 111 that has a hard point and raise it rounded? Okay. Could we take the V from Math 111, the absolute value, we did this in Math 105, you can ignore that. Absolute value, hard point, and make it a rounded curve instead, which would make it happier calculus-wise. What function does that? Which one? Pick one! Linear or quadratic? Which one makes it rounded? Quadratic, yeah? That's how statisticians got around the point problem. They said, oh, let's just make a new column that takes these and squares them. Now, Teresa's like, wait a minute, I don't like this. Good for you. Because I don't like it either, for a reason we'll get into in about 2 minutes. But for right now, let's just play with that. This is what happens. There's also a problem with this. This creates a problem we then have to remedy. But let's deal with that in a second. Okay, shall we? 1 squared? It's a tricky question at 11:15. You're probably all ready for lunch. 1 squared is 1. 2 squared? There we go, we're getting warmed up now. Negative 1 squared?
1.
Negative 2 squared?
4.
0 squared? Aha! Can we sum those up? Yes, we can sum this up. It doesn't give us anything useful. If we sum this up, we get x minus x bar all squared. We get 10, I think. I'm doing that right in my head. Have any of you ever read a research paper where you encounter something called SS, or the sum of squares? Does this ring a bell for any of you who have read research papers before, the sum of squares? Not yet. Some of you will. That is what's called the sum of squares. In other words, it's the sum. It's a shorthand for sum of squared deviations. If you take the data, deviate from the average, and then square them, that's the squared deviations. When you then add them up, it's the sum of the squared deviations. A lot of research papers report on that. I don't like stopping here for a number of reasons. Number one, why don't I like stopping here? And you shouldn't stop here, in my personal opinion, and most statisticians would agree with me as well on this one. Why shouldn't we just say, Ernie's 10? That's his number. We've got a number for variation, right? Would Bert's be bigger or smaller? Gut feeling, gut feeling. Bigger, good, much bigger, yes, much bigger. Why shouldn't we stop here? Tom, help me.
It's got the same issue where you don't, if you were just given the number 10, you wouldn't know whether it was 2 positive ones and 2 positive 4s.
We've got a bit of an issue there, don't we? We got a bit of an issue there. Because of the quadratic treatment of the distance, we don't know where the things are. Very nice, very nice. We also are going to over-exaggerate for greater deviations. Think about it. What's 1 squared? There's no deviation at all from 1 and 1, right? What's 10 squared?
100.
That's a huge deviation from 10 to 100, isn't it? So the more deviant you get, it gets exponentially blown up. We have to deal with that. And here's another thing we have to deal with. What are the units on these numbers right here? What's 82 what? 83 what? Points, right? Or percentage, whatever you guys want to call it. Percentages or points, yes?
Yeah.
If I subtract the average from those percentages or points, what are the units on these? Aren't they? Right? 1 point up, 2 points up, 1 point down, 2 points down. Fair? What are the units on these?
All positive.
They're all, what are they, what's the unit though? They're all positive. You got that, Lloyd, absolutely. What are the units? Are they? Is it? Or is it points? Be brave! It's points squared. What the hell is a squared point? What's a squared percentage? I don't know. I don't know what any of those things are. It's just, that's what it is though, right? I know, in 105 I tortured you guys with a whole project of dimensional analysis. I appreciate you for surviving through it. But it's one of those things, if you don't pay attention to the units as you go through this is now a different dimension. This is squared versus linear. Linear is 1 dimension, squared adds a 2nd dimension. You can't just add a 2nd dimension and then call it good. It's like saying the national debt, what, $17 trillion? Let's go ahead and square that, which they're on their way to doing, right? But then you have square dollars. What's a square dollar? That doesn't mean anything, does it? So what are we going to have to do at some point? This is what upset Teresa, I think. What are we going to have to do at some point during this calculation? Yes, yes, yes. Take a square root to get the unit back to just percentage points or percentage. But not yet. Not yet. Why? Mathematical reason I'll get to momentarily. What we're going to do is I'm going to give you a term we're going to refer to just in the moment because we need to talk about it just in the moment. It's called the sample variance. And it's so funny we're talking about this today because I just mentioned this in 244. And the next time we'll actually talk about this with any kind of seriousness is in 244. But we need it to get to the next step, which is what we talk about every day in here, which is the sample standard deviation. We need to get here first before we get down to where we actually need to be at the end, which is taking the square root and calling it good. So the sample variance, basically, what it does is, I'll get purple, it averages that sum of squares. That's the basic gist of what it does. So it takes that sum of squares that you just did, that sum of square deviations, and it averages it. Basically. So what would you do if you had to average that over your data? You would take the 10 and divide it by what? 2. Why 2? Oh, good. Why 2? Say that again, Teresa. Because what's in the middle? 2's in the middle.
No, it would be 5 would be in the middle, which would be...
Oh, you just said it. 5. There's 5 tests, right? So you would divide that 10 by 5 and call it good, because there's 5 tests. The sum of squares is spread over those 5 tests. You divide by 5. Oh, the number is 2. 10 divided by 5 is 2. You're 3 steps ahead of me. I'm sorry. Well, my question was, what would you divide by? You divide by 5 to get 2. I'm with you. I'm totally with you now. Totally tracked. Apologies. You guys think far too quickly for me. That's saying something as an East Coaster. So, yeah, you would divide by 5, right? That makes perfect sense. Makes perfect sense. You would divide that by 5. Mathematically, however, you're not allowed to do that. Because, and this is where it gets a little 244-ish, and I apologize. You can tell we don't like this already. More coffee, perhaps. If you divide by the sample size of 5, you do something called biasing the estimate. Okay, big step back. What are you interested in when you draw a sample? When you draw a sample, what are you interested in, Sandra?
The average.
Average of what?
The
You get your sample average.
Total sample,
But when you say total, what do you mean?
like the whole population.
Oh yeah, oh yeah, oh yeah.
Average of the whole.
Oh yeah, oh yeah, for sure. That's exactly what we want. We take a sample average, we get that sample average, but we're not really interested in the sample's average. We're interested in taking that sample's average and applying it to a population. Think of that Gallup quiz you did last week, right? The Gallup stops at 41% and you go, 41% plus or minus 4%, because the 41% probably isn't exactly right. So you slap the margin of error on there, call it a day. Yes. This is still a sample, right? If you had the entire population, you would divide by how many members were in the population. You would. Mathematically, that's simple averaging. But mathematically, and if you don't buy this, I don't blame you. If you do that with the sample, it comes out always a predictable amount off of what the true value is. It's always off by a predictable factor. I didn't believe that at all. When I sat in my first stat class, I said, no. So I went home and proved it. I was like, well, there it is. After 2 pages of mathematical proof. The proof I give as a gift to you on the page of the website called Enrichment. It's on there. Why do you do what I'm about to tell you that you do? This is the basic idea, yes? The technical idea is actually this. The technical idea is, now this guy right here actually has a shorthand name. We call him little s squared. Why? You'll see why momentarily. Teresa's already answered this question for us 10 minutes ago. This is how you calculate. You basically do this. You average the sum of squares. So you start by taking this quantity that's up top. You do that. Now logic would say you divide by your sample size. That's logic. Mathematics says your logic is a little bit flawed. You actually divide by 1 less. That controls that little factor. If you divide by n in the sample, you're going to always miss the population value by a factor. That controls for the factor. I don't expect anybody sitting in this room to believe that right now. Anybody watching at home to believe this right now. It's probably the single most tricky concept to buy in 243. It probably is, honestly. That's why I proved it for you and put it online. You can take faith in what I'm telling you, that it's true. I appreciate that if you do that. We also allow technology to crunch it for us and not worry about it. This is the only time you'll ever do this by hand, just FYI. But that is the correction. That's the correction to make sure that we swing back. Give you a quick example. Remember, a couple days ago, I put up Inigo Montoya's speech from The Princess Bride, and I told you guys to estimate what the average length of a word is in there. And you guys all guessed like 5 and 6 and 7 letters. The average is actually 4. 4 letters per word. Why did you guess so high? Because your eyes are drawn to the larger words. Your eyes have a bias towards the larger words. This controls the bias in the estimate of the variance. It's just a mathematical correction for what's called bias, which we spent a lot of time in 244 studying. Go then, go please.
So you said the sample variance averages the sum of the squared.
Mm-hmm.
So I'm having trouble with that because isn't there only one sum? The 10 is only.
Yes, ma'am. No trouble at all. Watch this. That means this is 10 divided by 5 minus 1, which is 4. No trouble at all. We just stopped before we got to the actual calculation part, which ends up being 2.5, right? 2.5. So if it's driving you nuts right here, sitting in this chair, I don't like that n minus 1, I encourage you, go to the original page, wander over there. I've got a nice mathematical proof for you. If you have trouble sleeping tonight, it'll put you right out, guaranteed. But I wasn't happy. That page is full of me being 20, 21, 22 years old, sitting in my stat professors must have hated me. I don't get that. Why? And it always resulted with, because I've been teaching it for 30 years and this is the way it's been. And I was like, I just don't like that.
Take faith.
So I started, well,
No.
I don't like faith when it comes to mathematics,
Yeah.
right? I like to know why things work. I don't want this to be a math class though. I want it to be a stat class, an interpretation class. So I put all that math offloaded to that website. So if you're interested, it's all there waiting for you. Either YouTube video form or an actual proof form. You can ignore that whole page if you want to. Tom, ask me that question.
Are we talking about variance here, saying like sample compared to population?
Yes.
So with Ernie and Bert, don't we have the entire population?
If you treat that as a population, yes.
Assuming like if we wanted to apply it to the
Yes.
6th.
Correct. What I'm trying to do is, I'm trying to give you the tool you need most often, which is you'll have a sample from the population. Sure, if you treat this as their entire population, this whole argument is moot. But in general, you have a sample, don't you?
Yeah.
That's why I'm trying to prep you for the sample. That's a great question. Did you hear his question? His question was, isn't this a population? You could treat it as such. I'd rather treat it as a sample because that's what you guys are going to have most likely, right? You're most likely going to have a sample drawn from a population. I'd rather give you that tool. Because this tool devolves into the other one as n gets larger anyway, so you're golden. Is that fair?
Yeah.
Hey, quick question. What's the unit on that? Oh, we're into the plus or minus, but the units as far as points, we're still at squared points. We're still at squared points. So we fixed that. We fixed that by, Teresa, finally, we fixed by doing what? Go ahead, you had it. Say that again? Sometimes that works, but we'll always get rid of the square. Yes, ma'am. Take the square root, and this is the sample standard deviation Chrissy mentioned earlier. This is the measure of variance I want this class to center around. The square root of that. This is called the sample standard deviation. This is the measure of deviation that I want this class to center around. I'm trying to separate it from the measures of center up here because it is definitely a different thing. But I'm out of board space over there.
So it's measures of century, you said?
No, I'm separating it from.
Okay. Like what? Okay, got it.
Is it just notated S?
It is. It's just called S, thank God. It gives a nice logical name for it. And it's found by taking the square root of the variance. So the only reason we need the variance now is to get the squared quantity that we then root to get the unsquared quantity. So it would be the square root of, what is that, 2.5 squared points, which ends up being about what? 1.6-ish? I'll buy it. And then we're down to just points and we're happy. Because that makes sense, doesn't it? It's back to points, which is the right unit. Stay with me. We got this. This is awesome. This is awesome. Good stuff. This is good stuff. Now, the most important part is not all this. This is annoying. I mean, I think it's mathematically beautiful. This is not a math class, though. This is not a math. It's a stat class. So what is the most important question to ask right now? Not if you can remember how to do this, because you'll never do this again. Tell me your name one more time.
Kevin,
Kevin, what's the most important question to ask?
what does that mean?
Oh! Say it again, Kevin.
What does that mean?
Oh, brother. That is the most important question I can think to ask right now. What? Are you all thinking that? It makes me very happy. Very happy. So, what does it mean? What does it mean? Jay, what does it mean?
That we can expect his next score to be within 1.6 points of the
Oh! Oh, you're taking it 2 steps, which I love, by the way. Thank you. Let's take it 1 step. Can we hold that for just a couple weeks? You're making it inferential. I don't want to make it inferential. I want to keep it just within the realm of these 5 test scores. I want to keep it in this sample. I don't want to go past the sample yet. I love where you're going with that. I want to go there. I do. I promise. But right now, let's just stay within the sample, okay? How does that 1.6 talk about my sample? That is such a good question. Thank you, Kevin. And you're all thinking it, which makes me even happier. What does it mean? Say that.
So the plus or minus that was speaking of.
Is this the plus or minus? Yes.
So
Give me.
his test will be above or below the 1.6.
Okay.
Or the average. I don't know.
Wait, no. You do. But it's not Renee.
No, it's whatever.
No, it's not whatever. Which one?
Howard.
Kelly. Where's my other Kelly? There's 2 Kellys in here, right? I'm totally making that up. It's Kelly.
There can be.
There can be. Well, there's just 1 Kelly right now, and she's saying something very important. 1.6 up or down? Or up or down? From what? Let's put it together. What we've just come up with is an average distance. The data points are from the mean. That's what you guys have just, you actually had done it back with the average deviation. It's actually called the average deviation. This 1.6, what this 1.6, let's turn the camera back over. You got, Kelly, you nailed it.